is the normal copula. So we know that to define a copula, what we do is we take the F, which is the joint CDF, at the U1. F K inverse U K. That is exactly what we do to get specific copulas, and in this case use each of the FIs as the normal mu I sigma I squared distributions, and the F as the k dimensional, the multivariate normal with the mean vector mu and the covariance matrix sigma, where they are related in such a way that the ith component of mu is mu I and the diagonals are sigma. So the marginals should match. The marginals of this are these. So start with the multivariate normal and then evaluate it at these marginals, and the corresponding copula you get is the normal copula. And how the normal copula looks, there are all the derivations and details. You plug in the distribution of F and so on and do that. So I am not copying those things, but I will write down the form of the density. So what the density means is you have the copula, which is this F of things, and then if you take the k times derivatives of the C, whatever you get, that we will call the density. And in this case the density exists because everything is multivariate, density exists there, continuous. So for the normal, the density is, you can write down explicitly what it is. This is the density copula. With C it's difficult to differentiate between small and capital. So this is do this with a psi. Just hold on, okay. So what you need is not the sigma, but from the sigma you need to go to the correlation matrix, and we'll call that the psi matrix. So what does the correlation mean? That for all the diagonals are 1 and the off diagonals are whatever sigma was, sigma ij, but you divide it by the sigma I sigma j. So if this matrix was sigma 1 squared, sigma I squared, and off diagonals for sigma ij, then you take the off diagonals, each off diagonal, and divide it by the corresponding square root of the diagonals, the standard deviation essentially. Okay, so that is called the correlation. So this is the correlation matrix that has all ones here and the correlations there, and this is in terms of that correlation matrix. So this is to the power minus half exponential minus half, and then there's another term here. I will introduce what that is. Transpose I inverse minus the identity matrix, and again this zeta, where the J is capital phi inverse of uj. Okay. So each component wise we take the capital phi inverse. Capital phi is the CDF of univariate normal. This is standard notation. This is the CDF of normal 0, 1. So everywhere we take the inverse of the CDFs as expected, but the way the form of the function comes out to be that times correlation matrix minus inverse minus the identity matrix and the quadratic form with that thing.
Correlation matrix, like the other elements, sigma ij divided by all the standard deviation, right?
It's divided by the corresponding I and j. I at j. Right. Right. We haven't talked what correlation is. So that is the definition of correlation. That we have said that the covariance is sigma ij. So if you divide the covariance by the standard deviations, then what you get is called the correlation. Maybe I will just state that anyway. That's not in. So covariance of xy is the expectation of xy minus ex ey. That the form we used, or maybe we use this form, x minus ex, y minus ey. Right? Covariance we define this way. So this is sigma ij. This we did when we were doing multivariate normal. Sigma I squared is expectation x minus ex squared. This is sigma j squared. Not xy but xi xj. xj, xi, xi, xj. Now if you look at sigma ij over sigma I sigma j, that is denoted by rho ij, that is the correlation between xi and xj. Okay. So with all the different notations explained, the final result is this, that the density of the normal copula looks like this.